and this is clearly greater than equal to the minimum over any possible L being an integer greater than equal to 1 of 1 minus 1 over L whole raised to L times ZLP. Okay. So the quantity that we have outside over here is our approximation factor. And what is the minimum over this? We notice that 1 minus 1 over L raised to L is maximum when k tends to infinity. Okay, or rather, sorry, L tends to infinity. And this limit goes to 1 over E. So the expected weight of satisfied clauses is at least 1 minus 1 over E, because the quantity 1 minus 1 over L whole raised to L is maximum. So 1 minus this quantity is minimum, and the minimum value is 1 minus 1 over E times ZLP. Okay, and this is nothing but the expected value of our algorithm. So this is significantly better than our half approximation. It's a 0.63 approximation found by rounding the linear program. Now, if you notice, then the linear programming approximation that we have just derived and the initial purely randomized algorithm are very different in two ways. In the following way, that is, for the randomized algorithm, the expected value, or rather the probability that a clause is satisfied, increased with the length of the clause, right? And so, whereas for our particular algorithm over here, based on the rounding of the linear program, the probability that Cj is satisfied looks something like 1 minus 1 over Lj raised to Lj times Zj star. Okay. And this quantity here decreases with the increase in length. Okay. So what this means is that our randomized algorithm does well when the clauses are large, and the LP based randomized rounding algorithm does well when the clauses are small. So what we should look to do is try to combine both of these algorithms in some way. And the most natural way of combining is the following. Okay, run our randomized algorithm. Get W1 is equal to weight of satisfied clauses. Okay, and W1 is a random variable, again depending upon the random coin toss outcomes that came out. We run the LP randomized algo. And get that W2 is the weight of satisfied clauses. And what we do is choose the best assignment out of the above two. Okay, so it's as simple as it gets. Our randomized algorithm gives an assignment, the LP randomized rounding gives an assignment, and we just choose the best of the two. Why does this work? We'll see that this gives a 3/4 approximation algorithm. Okay, and here's a proof. Let W be the max of W1 comma W2, and the expected value of the algorithm, nothing but the expected value of W, right? And what is this equal to? Well, this is at least half times the expected value of W1 plus W2, right? Now, what I'm going to do is use linearity of expectation and substitute for the W1 and W2. And notice that both of these quantities we have already computed in the previous video. Okay? I'm going to write this as summation equal to 1 to n. So this is what the randomized algorithm gives. And this is what the LP based algorithm gives. Okay. Again, I've used linearity of expectation in doing this. Ideally, there should be a summation over here, which gives me the LP based algorithm, but I've just pulled the summation all the way outside. Now, I'm going to introduce a ZJ in between because it does not really matter. And this over here I've added in because ZJ star is always less than or equal to 1. It doesn't hurt to add this in. So now what I'm going to do is again do what we did before. Write this as greater than equal to 1 of this big function, which is 1 minus 1 over 2 raised to Lj. Well, there's no j here because we'll just take the minimum over all integers as before, times, well, what's remaining inside is j equal to 1 to m of wj zj star, and this is nothing but zlp. So the whole thing boils down to finding the minimum of this function. Okay. So the way to do this is actually simple, that we can just enumerate over the possible values that L takes. Okay. So you just compute it for L equal to 1. Well, if you actually substitute in the values, you'll find out that this takes the value 3 halves. Again, for L equal to 2, it takes 3 halves. And for L greater than equal to 3, we have that the second quantity, rather first quantity, is greater than equal to 7 by 8, and the second term is greater than or equal to 1 minus 1 over e, and if you add up this is greater than or equal to 3 over 2. Okay, so coming back, the expected value of what the algorithm outputs is at least half times 3 over 2 times ZLP, which is at least 3 over 4 times ZLP. Okay, so this is better than either of them. Okay. So choosing the better of the two solutions is a 3/4 randomized approximation algorithm. So you might ask if we can just reproduce this result, a 3/4 approximation, using simply randomized rounding. The answer is yes, it will be part of your homework assignment. Now let's move on to the next problem, which is the price collecting Steiner tree problem. Okay, so recall the definition of the price collecting Steiner tree problem. We have referred to this as the cable connection problem. So the input is a graph V, where you have costs on the edges, the costs are non-negative, and we have a penalty on the vertices. Okay, so the penalty is applied to vertices that you miss out on. So there's also a special vertex R, and you can think of the problem as extending a cable connection from R to various houses in the neighborhood along the edges. So the more houses you cover, the better it is, but you also use more length of cables. But if there's a house really far away, you might as well say I'll just skip it, and for skipping it I'll encounter some penalty. So for skipping a vertex I, you get a penalty pi I. So finally what you want is a tree which will contain a subset of vertices which I call V of t, and it should contain R. The objective consists of two parts. The first is the connection cost, and the second is the penalty for skipping vertices that you don't connect in your output tree. Okay. So now what we had seen previously was a three-factor approximation where we use deterministic rounding and a primal dual algo for constructing a Steiner tree on a set of points. Okay, so this was part of your problem set 4. Now what I'm going to do is go over the deterministic rounding scheme very briefly. So in the algorithm, we first write the LP. So the LP relaxation that we use is going to be the same, so I might as well write it. So the LP has variables for every edge, and X is the indicator of whether E is in the T or not. And then you also have variables Yi for each I, whether I is included in the vertices of the tree or you skip I. Okay, so on the basis of this, the LP objective is going to be the minimum over the assignments of variables, connection cost incurred, plus a penalty for the vertices that are skipped. What are the constraints? Well, if you recall, most of these tree problems had got an exponential number of constraints. This was no different. We had given a separation oracle for it. So you pick out some subsets such that R is in the subset and the vertex I is not in the subset. Okay, and if I was included in our final vertex of the tree, then there should have been an edge which crosses the set R, which crosses the set S and connects R to I. So there should be at least one edge on the cut, which is 1 if yi is selected. Okay, if I is selected, if yi is 0, then it does not really matter. Now, if you don't recall this LP clearly, it's fine. We are not going to use it in too much detail. What we'll need is basically the algorithm from before. So we're going to solve the LP and get the optimal solution, which are y stars, x star, and the value as usual is ZLP, which consists of two parts, of course, the connection cost and the penalty cost. You look at the set of vertices which have large yi value. And on them, you build Steiner tree using the primal dual. So you just look at the i's which are large yi value and build a Steiner tree on them. And we had the following true properties that we wanted to check. So this is all. You build a Steiner tree and you output t. In the analysis, we had shown two crucial facts, that the Steiner tree that you so build has a cost that is comparable to the LP connection cost. Okay, so notice that the alpha that you use for thresholding the vertices turns up in this. And this was your homework or problem set 4. I think it was the very first question. The second thing that you wanted to check that the penalty cost that we incurred again is related to the penalty cost of the LP over a factor 1 minus 1 over alpha. Now, the point is, in the deterministic rounding scheme at this point we had chosen an alpha or set alpha such that 2 over alpha was equal to 1 over 1 minus alpha, which gave us a C approx. Okay, because the first one was decreasing in alpha and the second is increasing in alpha, so we wanted to balance out the two. Okay, so this gave us a 3-factor approximation. Now what we're going to do is actually, so notice that alpha is set at the very start of the algorithm in step 2. Okay, and depending on the alpha that we set, we are choosing the set U and building a Steiner tree T. Now here's another way in which we will actually choose the value of alpha randomly. So I'm going to introduce parameter gamma, which I will specify later. Right now all you need to know is gamma is less than 1. So we'll see what is an appropriate value of gamma later. We'll choose alpha uniformly at random from the interval gamma comma 1, and then we will run the above algorithm. So notice that because the choice of alpha is random, the penalty incurred and the connection cost incurred by the algorithm are also going to be random depending upon alpha. So we're going to go ahead and analyze this. In fact, we're going to analyze what is the expected connection cost incurred by the algorithm and what is the expected penalty incurred by the algorithm. So let's look at the connection cost first. So what is the expected value? The connection cost is nothing but the expected value of summation of the cost of the edges that are included in the tree. Okay. Now we know that the cost of the edges included in the tree is at most 2 over alpha times connection cost specified by the LP, and this we got just using 0.1. The only new factor over here is the expectation because alpha is random. Okay. Now this is equal to the expected value of 2 over alpha times our usual factor. So what is this quantity? Now alpha is randomly chosen, so UAR means uniformly at random. The expected value of alpha is going to be expressed by an integral. So here's your interval from gamma to 1. So of course every point here has a probability density of 1 over 1 minus gamma. And so the expected value of a function so it is the obvious thing. In case you're not familiar with this kind of notation, it's fine. The integral should be clear enough what we are doing. The alpha of course can't come out, just 1 over 1 minus gamma times d alpha, right? And if you integrate this out, you get the 2 outside, 2 divided by 1 minus gamma of ln alpha going from gamma to 1, which turns out to be 2 over 1 minus gamma times natural log of 1 over gamma. So this is just I'm using some facts on conditional expectation, which I assume you're familiar with. Sorry, continuous expectation. Okay, so now the expected value of the connection cost that we incur is therefore equal to 2 over 1 minus gamma times log 1 over gamma times summation over E. And notice what you have gained here. We have gained this factor over our deterministic algorithm. We next go for the penalty costs. Okay, so what are the vertices that we leave out? Okay, so notice that we are doing the thresholding in the following way. We are choosing a random number between gamma and 1, okay, and setting that to be alpha. Now, if there was a vertex I with yi star which is less than gamma, then already we will have the fact that 1 minus yi star is greater than or equal to 1 minus gamma, and vertex is not chosen, or rather vertex is penalized with probability 1, right? So these vertices always occur in the penalty. And if yi star is greater than gamma, then what is the probability that I occurs in the thresholded set of vertices U? Well, it is exactly the probability that alpha is in yi star comma 1. Okay, and this probability is equal to 1 minus yi star divided by 1 minus gamma. Therefore, the expected penalty is exactly equal to for these vertices you always incur a penalty yi, and for the vertices which have yi star values which are greater than gamma, you incur an expected penalty cost right. But notice that because of the observation above, this at most the second term remains as it is. All I'm using the fact is that 1 minus yi star divided by 1 minus gamma is greater than or equal to 1 if yi star is less than or equal to gamma. Okay, so the whole term is simply less than or equal to 1 over 1 minus gamma times summation over all I, irrespective of whether the yi star value is less than gamma or greater than gamma, of pi I times 1 minus yi star. Okay. So we have bounded both our connection cost as well as the penalty of skipping vertices cost that is output by the algorithm. So the expected cost of the algorithm is the expected penalty, rather the expected connection cost plus the expected penalty cost, which is at most 2 over 1 minus gamma log 1 over gamma of DLP value plus sum over vertices of pi I times 1 minus yi star divided by 1 minus gamma. So this is cool, and right now what we are going to do is do something similar to what we did in the deterministic case. We have a trade-off on both counts and we are going to balance it using an appropriate value of gamma. So you balance both terms when 2 over 1 minus gamma times natural log of 1 over gamma is equal to 1 over 1 minus gamma, which gives us that gamma is e raised to minus half. So this implies that substituting this value of gamma, finally get that the expected value of the algorithm is at most 1 over 1 minus e raised to minus half times ZLP. Okay, because what remains back when both of these terms are equal and you pull it out is just the LP value. So this is approximately equal to 2.54 ZLP. Of course, this is a fraction of some sort. This is a irrational number of some sort. So this is 2.54 randomized approximation algorithm. So one common point between both of the algorithms that we have seen, by both I mean the one for MaxSat and one for this, is that the algorithms can be de-randomized. MaxSat and PCST. That is, based on this randomized algorithm, you can come up with a deterministic algorithm that gives the exact same performance guarantee. So I'm going to skip the details of how this is done. But notice that analyzing the randomized algorithm is also much easier than what it would have been for the corresponding deterministic algorithm. Okay, so that's all I wanted to say about these two problems. Now the next problem that we'll move on to is the minimum congestion routing problem.